Normal stimulus and response for UDP traffic is fairly straightforward. Now, we're not going to talk about the IP addressing and things like that because that was in relation to the network layer, and all that stuff is still happening. Remember, all these layers are working kind of concert together. All these different protocols are working together to make sure this communication happens. But here we're going to focus specifically on the UDP or transport layer aspects of that communication. In this case, we have system A with an IP address, we have system B with an IP address, and system B happens to be running the DNS service on UDP port 53. DNS generally relies on UDP, although it can use TCP in some circumstances, but for our purposes, we're talking about standard DNS over UDP on port 53. That means there's a DNS server service listening on system B, and that service is bound to listen to requests on port 53. So if system A wants to communicate with system B on DNS, it has to send data to it on that port. So that's what we have with the case of our DNS request. In this case, system A picks a random source port. In this case, it picked 3724. Notice that that's above 1024. It's one of those ephemeral ports. And it's chosen to send data to destination port 53. And that's how, when system B receives this information, that's how it knows what application will be handling it, because there's an application, in this case a DNS server, bound to port 53 to process that data. Now, there doesn't have to be a response here if this was a protocol that didn't require one. But in this case, DNS generally requires a response because this is probably a DNS request, so there should be a DNS response with the appropriate data. When this happens, the source and destination port are simply reversed. So system B transmits data back to system A with a source port of 53 to the destination port 3724. The whole purpose of system A specifying a source port when it sends that data is so system B knows how to send that data back so that system A can process it normally. Any given system is communicating out to the internet or to other devices all the time, a bunch of different things going on, and it's via these source ports and destination port pairs that we can track the communication on a per conversation basis. If you watched the Wireshark section earlier where I showed you the conversations window, you remember we looked at TCP and UDP, and we saw that we could define individual communication, conversations, and streams by the source and destination port combinations along with the layer 3 IP addresses, and that's what we're talking about when we're looking at normal UDP stimulus and response. Let's look at another scenario, but in this case, we're going to look at a port unreachable scenario. In this case, we have system A and system B again. However, in this case, system B is not a DNS server. It has no port 53 service listening. There's no service listening that's bound to port 53 and it is configured to accept requests. So there's a number of reasons system A might want to communicate with system B thinking it's a DNS server. Maybe the DNS server address that was put in was incorrect. Or maybe system B actually is a DNS server, but that service is down and it's not up, it's not responding to communication. There's a number of scenarios that could be at play here. In this case, system A will send a packet to system B with a source port of 3724 and a destination port of 53. If system B isn't listening, has no service bound to 53, what's it going to do? Well, it's not going to process the data because it's got no way to do that. It's got no service that's ready for it. So in this case, it's actually going to send a packet back, but not a UDP packet. It's going to send an ICMP packet. We've talked about ICMP and how it's kind of a utility protocol, and one of its utilities in this place is to respond with a type 3 code 3 message, which means destination unreachable, port unreachable. And that's how system A knows that system B is up and alive and responding, but it is not responding via communication on port 53. There's no service listening and ready there to accept that communication. So you see a UDP packet out and an ICMP packet back. You won't see a UDP packet back that's indicating some sort of error state because that's not a feature that UDP provides. I want to go through one other scenario related to this port unreachable type event that we're talking about. And we'll say we have the same system A and system B, and I send traffic to system A from system A to system B, but there's no service bound to it. That port is not open. So let's say you're looking at this from the perspective of system A and you're actually capturing packets, and you see this packet go out and you wait for an ICMP message back or a successful response back, but you actually don't see anything. You don't get a single response back. Is this normal? Well, it actually is, and for a couple of reasons. One thing to keep in mind, and this is related to our conversation on ICMP earlier, is that some systems are configured simply not to respond with ICMP messages to certain types of probes. They have host-based firewalls on them that prevent them from doing that for various reasons. This image, how it's depicted here, shows a straight line, but System B could actually be on another network. If System B is on another network, there may be routers in between those systems that are not configured to allow ICMP messages back. So there's a number of scenarios, as we discussed, that will not allow ICMP to come back to a system to report an error like this. So it's very plausible that if you send a packet to a System B like this in this example, you to a port that's closed, you won't get any response back at all. And also keep in mind, this very same thing could happen in some cases where System B doesn't exist. You could send a packet from System A to System B to a specific port, and that system isn't turned on, or it's off, or it's down, or some other thing is going on, and you're not going to get a response back at all in some cases because there's nothing to send an ICMP response, and even if it were, maybe it is getting blocked by something intermediary. So that's the thing you have to be careful about with ICMP, is you may not always get the responses back you expect. But what you would have to know here is at some point, if you send UDP data out and get nothing back, then something is wrong and additional troubleshooting generally has to occur. The only abnormal stimulus in response I want to talk about for UDP is an occasion when there's a bad checksum. So this is the same scenario we've been looking at. In this case, DNS is up and running on System B and is listening on port 53, so it's accepted the traffic. But in the case where it receives traffic and calculates the checksum and it's different from what's in the packet using all the same processes we've already discussed, that is actually going to be silently discarded and no response is going to be sent back. So you're not going to see an ICMP message. You're not going to see anything of the sort. You'll just won't see a response back. So the interesting thing here is this looks the exact same as the occasion we just talked about, wherein the system is down or is not listening on port 53, but something is blocking ICMP messages on the way back. So it's very easy to conflate those two, and you don't really know if it's a checksum issue or if it's a down system issue or down service issue. Now, practically speaking, we don't see a lot of bad checksums anymore. That's just not something we see a lot of. Routers are generally going to calculate those just fine. In some cases, the checksum could be calculated by found to be bad by a particular router, and maybe it's going to let you know. But generally speaking, if you see this type of stimulus and response, it's most often not a bad checksum. It's actually a case of down service, down system, and ICMP being filtered on the way back. But I do want you to be aware that when a bad checksum does exist, it's typically silently discarded by a recipient system. I've switched over to Wireshark now because I want to show you an example of a couple of different UDP transactions. And sticking with the theme of the examples we've been using, we'll stick to DNS data, which generally relies upon UDP. In this case, we have two packets. It's a simple transaction from 192.168.0.114 to 205.152.37.23. We see in the info column, this is a standard query. And then on the second packet, we see that the source and destination addresses are reversed, and we have a standard query response. So even without understanding DNS, you know that this is a pretty simple transaction, simple request and response. Now I'm going to look down here with packet 1 selected into the packet details window, and we see we have our data link layer protocol Ethernet, our network layer protocol, which is IPv4, and then we have our transport protocol, which is UDP. Of course, below that, we have an application layer protocol, which is DNS, but we're going to focus on the UDP protocol and expand that here. In this case, we have the 4 fields we expect to see: source port, destination port, length, and checksum. Our source port is 1060. That's an ephemeral port that was chosen by the source computer, so 192.168.0.114. It was chosen by that, and it was sent to the DNS service, which is listing on the recipient at port 53. And you see we have transport resolution turned on. In this case, it tells us that 53 is usually associated with the domain service, or in this case, the domain name service. This source port is sometimes apparently associated with something called Polestar. That doesn't necessarily mean anything to me, and maybe it doesn't to you either. So I would generally just ignore that for most ephemeral ports unless you know that you're looking for a specific thing. Nonetheless, we have a source port and destination port. Of course, if I click in the second packet, you'll see that those switch. Source port is now DNS, destination port is now the ephemeral port 1060. We have length field. In this case, the length of this packet, it's not a very big one. It's 39 bytes, which is the UDP header size plus the DNS query. In the second packet, we see that the length is 55 bytes, so it's a little bit longer for a response, which makes sense. We're making a simple query, and the response is actually going to be a little bit more data. Beyond that, we have the checksum fields. We don't have checksum verification enabled here, so it tells us it's unverified. But nonetheless, we do have those checksums available, and that really is it. That's the extent of the UDP header. It's very small. I'll highlight it here. You'll see it's only those 8 bytes that are highlighted in the packet details window. So very straightforward, very simple, and this is an example of the normal stimulus and response for an application layer protocol that relies upon UDP at the transport layer. I just switched over to another file called udp_DNS_request.pcap. And I want to show you this one because it highlights an issue we talked about earlier with non-responsive UDP requests. In this case, we only have one packet. It's from 192.168.100.138 destined to 192.168.100.1. We see it's a standard DNS query. I'll go ahead and expand the UDP protocol header, and we see it's also source port 1060, destination port 53. However, we don't get a response back. And since this is DNS and this is a DNS query, we definitely expect a response back. So where is the response? Well, that's an awfully good question. We don't have anything back that tells us what it is. We don't have an ICMP message telling us that the port is closed, and we don't have anything that can tell us whether the checksum was valid. And for that matter, we don't know how many networks are separating these two. We can probably make a guess they're in the same subnet here, so it looks like they're probably on the same network. But in another situation, you might not know if there are routers separating you. So from the source, and I'll tell you this was captured from the source, you actually don't know what the deal is. You don't know what the problem is. So that would require further investigation. Now I would ask you, how could you investigate this further? And we'll look at an example of this when we get to more practical scenarios later. But if you encountered this where you have a DNS request going out and you see no response back whatsoever, how could you troubleshoot that? Well, the answer is going to be, if at all possible, is trying to capture packets and capture these requests actually on the DNS server itself or on some intermediary box. If you're capturing on the DNS server itself, you can actually see if it's receiving packets with bad checksums. You can actually see if it's receiving the packets at all, and maybe there's something else going on, but that's going to be your answer. Generally, and that's going to be a pretty good recommendation all the way across the board, is if you're capturing from a source and you don't have enough information to make a good judgment about what the problem is, maybe you need to capture at the destination or at minimum some intermediate step along the way. But nonetheless, these are a couple of examples of very basic UDP communication. Very simple, very straightforward. Here in a minute, we'll get into TCP, which is a much more involved subject.